This is Daniel Coosbury, and in this video, we're going to look at some components of a hypothesis test. So this video is still introductory for hypothesis testing, and we're looking at probably maybe most of the components of a test while keeping it as general as possible. So this is going to apply to all the different kind of hypothesis testing you're going to do. But there are a few components that aren't in this video that are specific to different search situations. So it's going to change whether we're doing like a hypothesis test for the mean and we do know sigma, or if we don't know sigma, or if we're doing something for the proportion. There are special components for each one of those, and they'll change. So they're not in this video. This is the one that'll kind of help you do any kind of them, and you can learn the specific ones in the later videos. So let's start with the two definitions. So when you do a hypothesis test, you're always going to state two hypotheses. The first hypothesis is called the null hypothesis, and this is the one we're going to assume is true for the whole test. So we're going to pick a null hypothesis, which is going to say something about a parameter, and we're going to assume that it's true the entire time. So usually we would denote it with an H with a little 0 down there, and we would say that let's just assume that mu is equal to some value like 5, in which case we would call 5 mu naught. So the little 0 notation means that this is the value of the mean that we're assuming under the null hypothesis. We'll call that mu naught. So in general, you could write this as mu equals mu naught for the null hypothesis. So we're going to assume this is true the whole time. So as we work through some math and do the hypothesis test, we're going to have a stand-in number to see if this is true. And we're going to spend the whole test trying to see if this is true or if we should just throw this out and pick a different hypothesis. That different hypothesis is called an alternative hypothesis. It's denoted two different ways. It's denoted with H with a little a, or it's denoted H with a 1. It's just personal preference. Different people use different things. I'm going to use H1. But it denotes the alternative hypothesis, which is what we will conclude if we reject the null hypothesis. So we'll start out with this. And if we have enough evidence to say, yeah, that's probably not true, then we'll pick the alternative hypothesis. So there's a difference. We're gonna use this one the whole test, and then we're gonna decide if we should throw it out or not. And if we can throw it out, we'll pick the alternative. There's 3 different kinds of alternative hypotheses, and they determine 3 different kinds of tests of hypothesis tests. So let me say that again. There are 3 kinds of alternative hypotheses, and they determine the 3 different kinds of tests. So the first kind of test is a left-tailed test. It states that the parameter is less than the value specified by the null hypothesis. So we think mu is equal to 5. A left-tailed test would say, well, if that's not true, then we're going to say mu is less than 5. So maybe we think this is true, but we have to start out with a null hypothesis. The left-tailed test would say mu is less than 5. So the less than corresponds to the left tail. So think like left side, less than. The alternative hypothesis looks like this. So you would use that one. In the same vein, there's a right-tailed test. So the right-tailed test states that the parameter is greater than the value specified. So in a right-tailed test, if our null hypothesis is mu is equal 5, our alternative hypothesis is going to be that mu is greater than 5. So there's the greater, the right tail, those go together. This is how you write your alternative hypothesis if you're doing a right-tailed test. Now, sometimes I'm going to refer to these as being one-tailed tests. So this is just a general term for either one of these. Like this is a one-tailed test, that's a one-tailed test. And that's just to distinguish them from the third type, which is a two-tailed test. This states that the parameter is not equal to the value specified by the null hypothesis, and this is what this looks like. In a two-tailed test, you would say, well, if your null hypothesis is mu is equal to 5, your alternative hypothesis is mu is not equal to 5. And the reason this is called a two-tailed test is because here you're checking, you're going to say it could be bigger than 5 or less than 5. So right tail or left tail. It could be bigger or less. We're just saying it's not equal to. Here you're only saying it's less than, so that's where the left tail comes from. Here you're only saying it's greater than, that's where the right tail comes from. Here you could say, well, it could be either one. It could be greater than, it could be less than. And a good way to say it could be greater or less is to say it's not equal. So that's where the two-tailed comes from. There's the one-tailed thing down there. So left-tailed and right-tailed are called one-tailed hypotheses. I'm gonna make a couple videos in the future. One of them is going to be for a one-tailed test. One of them is going to be for two. They're nearly identical, but there's a big distinction in how you draw your normal distribution pictures or your t-distribution pictures. So I like to think of all the one-tailed tests as behaving one way and the two-tailed test as behaving the other way. So let's see if we can write down our hypotheses and identify the kinds of tests. So we have boxes of cereal of a certain kind are labeled as containing 20 ounces. An inspector thinks the mean weight might be less than this. So we're going to state the null and the alternative hypothesis. Now let me say something because I don't think I've said it yet. The null hypothesis always says mu is equal to some number, whatever that number is. There's always an equal sign there, I guess is what I'm trying to say. So notice in the alternative hypothesis, you have like a less than sign or a greater than sign or a not equal to sign. But every time I wrote these pairs, there's always an equal sign on the null hypothesis. So this is really important. This is the convention. This is how it works. We're always going to put an equal sign there. The alternative hypothesis is the sign that's going to change. It could be this one. It could be that one. It could be that one. I don't think I said that. So from that, let's go ahead and write our null hypothesis for this. So they are supposed to be 20 ounces. I like saying, let's just say they're supposed to be 20 ounces. So the one with the equal sign is going to be the null hypothesis. Now, the inspector thinks it may be less than 20. So how about we let the alternative hypothesis be less than 20? So then when we go do the hypothesis test, which we're not doing in this video, but when we go do it, we're going to assume this is true the whole time. And at the end of the test, we're either going to say, all right, it's 20, just like it should be. Or we're going to say, no, it's not. It's less than 20, like the inspector thought it would be. So those are two different conclusions. We either keep the null hypothesis that it's 20, or we get rid of it and we say, no, it's this thing instead. Let's do another one. Last year, the mean monthly rent for an apartment of a certain city was $800. A real estate agent thinks the mean rent is higher than this. So we're going to state the hypotheses. So this is also a one-tailed test. Mu is equal to 800 is the null. So you know it's the null because it has an equal sign. You should never put an equal on the alternative hypothesis. You should always put the equal there. Since the agent thinks it's greater than, let's do greater than. Let's do mu is greater than for the alternative. So this is also one-tailed. We'll call this a right-tailed test. Let's go back and call this a left-tailed test. And the left-tailed comes from this less than sign. So the left corresponds to less than, the right corresponds to greater than. And here's the last examples. We got a score on a standardized test have a mean of 70. Some modifications are made. Education, I'm sorry, I can't say that word, and I'm an educator. An educator believes that the mean may have changed. Okay, so here's this word changed. It doesn't say the mean rose. It doesn't say the mean has decreased. It says the mean may have changed. So this is an example of a two-tailed test because the mean was this, and we think it's changed. We're not saying whether it's bigger or smaller. We just want to see if it's changed at all, bigger or smaller. So we got a two-tailed test because we got a not equal to sign. That makes it two-tailed, bigger or smaller. The word changed is the giveaway here. This could mean bigger or smaller. So this is a two-tailed test. So that's how you write hypotheses. Once you do a few of these, they're going to get more comfortable. Like I said, the less than, the higher, and the less than, they kind of give away what you do. The change is probably the weirder one, but since this doesn't suggest bigger or smaller, use the not equal sign. Make it a two-tailed test. Now, based on the evidence from our test, which we're not doing tests in this video, we're going to draw two kinds of conclusions based on our hypothesis. Either we're going to have enough evidence to reject H naught, or we're going to fail to reject it. So let me draw you a picture real quick, or just write some things down here. So let's go with, we think mu is 5. The alternative is going to be mu is, well, let's just say it's bigger than 5. I just made it up. So either we're going to reject H naught, in which we assume this is true the whole time, and then something weird goes on, so we're like, nah, this can't be true. And our conclusion is going to say the mean is like, we have evidence to say the mean's bigger than 5. Like, we know that. The other conclusion we're going to draw is, well, we assumed this was true and nothing weird happened, so we're okay. We're going to fail to reject H naught, which means we're not like 100% sure this is true, but we don't have any reason to reject that. We're going to fail to reject it. Okay, so we're not necessarily going to say this is absolutely right, but nothing weird happened. There are no problems, so we're going to say that, okay, we're going to fail to reject H naught. Let's just hold on to this for a little while. Okay, so that's kind of, I guess that's what this slide says. If we reject H naught, we'll conclude H1 is true. If we fail to reject it, we'll say there's not enough evidence to conclude H1 is true. Note that we're not saying that H naught is definitely true. We're never going to be able to say that. We never know what mu is. We're never sure. We're statisticians. We're never sure about anything. We could be sort of sure, but we're not like completely sure. We are saying that H naught could be true, and we don't have enough evidence to the contrary. So that's kind of how the conclusion will be worded. So let's look at some examples, and I have some sentences that give you some language. Boxes of a certain kind of cereal are labeled as containing 20 ounces. An inspector thinks the mean weight may be less than this, so he performs a hypothesis test of H naught is equal to, mu is equal to 20, and H1, mu is less than 20. So we got that, and we got that. He rejects the null hypothesis. He rejects this. So he's like, nah, that's not true. So his conclusion should say, okay, this is true. Like, we have enough evidence to say that's probably not true. This is true. So because the null hypothesis is rejected, we're going to conclude that the alternative hypothesis is true. So we can say, this isn't true. Let's go this way. We conclude the mean weight of the cereal is less than 20 ounces. So what you're probably finding frustrating right now is I'm using a lot of new language from this video. I'm like null hypothesis, alternative, reject, like things like, and there are usually two ways to state your conclusion, and they're both good. The first sentence has this new statistics language. The null hypothesis is rejected. We conclude the alternative hypothesis is true. The second sentence interprets that for people who haven't taken a statistics class and don't know what any of these words mean. So this puts it in context. We conclude that the mean weight of cereal is less than 20 ounces. This is a really helpful sentence. This is something worth reporting to a supervisor, saying this machine is working the way it's supposed to because the boxes of cereal have, on average, 20 ounces of cereal in them, and that's good. So notice this first sentence has statistical language, and it's good and helpful. This second sentence does not have any statistical language. It interprets your conclusion in the context, which is also helpful. Okay, let's look at a different result of the same situation. So in this case, we're going to do the H naught is equal to, mu is equal to 20. H1 is mu is less than 20. He does not reject H naught, so we're going to state a conclusion now. So if we don't reject this, remember, we're not going to say, this is definitely true, but we also can't reject it. So what we say is, because the null hypothesis is not rejected, we do not have evidence to conclude the alternative hypothesis is true. So we can't say that. We just can't. Notice I've put a square around this. I don't have any reason to put a square around that rectangle. In other words, we'll state there's not enough evidence to conclude the mean weight of cereal boxes is less than 20. We can't say that. Okay, we're not 100% sure about this, but we do know there's not evidence to say this, so we'll hold on to that one. I know it's kind of flaky language, but that's what we're stuck with the statistics. We're a little flaky. So those are the two kinds of conclusions and how to say them. There's also a couple ways to be wrong when you do this, and when we're dealing with data and parameters that we're never going to know the value of 100%, there is a probability we're wrong. A lot like with confidence intervals, if we made a 95% confidence interval, for instance, then the chance that we're wrong is 0.0. Like, there's a 5% chance that our interval doesn't actually have the mean in it, for instance. So like, we're okay with this we're okay with this probability of being wrong because it's happened before. We're never going to have 100% certainty if we're doing statistics. If you had 100% certainty, you wouldn't need to do statistics. There are two ways in which a wrong decision may occur, and I think this flow chart kind of represents that well. So let's first off, if H naught is true and you reject it, then you've committed what's called a type 1 error. If H1 is true, if H naught is true and you don't reject it, then you made the correct decision. So this is true, you don't reject it, then that's a good call. If H naught is not true and you reject it, then you've also made the correct decision. So if this is false and you say, no, we're not doing that, then you've made a correct decision. If H naught is false and you fail to reject it, that means like, well, it may not be true, but I don't have any reason to reject it. You've committed what's called a type 2 error. So these are two terms worth jotting down and keeping straight. So this is if H naught's true and we reject it. This is if H naught is false and we don't reject it. So there's two different ways to be wrong. It's unfortunate. It's just true. So let's see if we can identify some errors and if we're right or not. So the dean of a business school wants to determine whether the mean starting salary of graduates of her school is greater than $50,000. She'll perform a hypothesis test in which the following null and alternative hypotheses are these two things. So notice the null has an equal sign. It always should. That's good. So the greater than comes into play on the alternative. So you end up with a right-tailed test. Suppose that the true mean really is 50,000. So suppose that H naught is actually true and the dean rejects it. So this is true, but the dean rejects H naught. Is this type 1, type 2, or a correct decision? Well, the null hypothesis is true because the mean is actually 50, but the dean rejects the null hypothesis. This is a type 1 error. You can look back at that chart and see what I mean. So H naught is actually true. The mean really is 50,000, but the dean's rejecting it, so you got a type 1 error. The dean's wrong. Let's do it again. So we have the same thing. The dean wants to test whether the mean is greater than 50,000, so the null hypothesis is the same. The alternative hypothesis is greater again. Suppose the true mean is actually 55,000 and the dean rejects H naught. In other words, the null says it's 50,000. The true mean is 55,000. So in other words, this is wrong because the true mean is 55,000. So suppose H naught is wrong. It's not true. And the dean rejects H naught. Well, this ends up being correct because this is not true. This is true, which actually is in favor of the alternative hypothesis. So if this isn't true and the dean rejects this, that's a good call, and the dean ends up being correct. Let's do it one more time. Same hypotheses. Suppose the true mean is 55,000. In other words, this isn't true, again, and the dean does not reject H naught. In other words, again, this is false because the mean is 55,000, but the dean doesn't reject it. The dean should reject it because it's false. It's really 55. But anyway, the dean doesn't, which is always possible. This is what's called a type 2 error. And we can look back at that table to kind of see how this is classified again. A type 2 error is when H1 is false. So H naught is false. So we're saying the mean's 50,000. It's really 55. So our hypothesis is false, but the dean fails to reject it. You got a type 2 error. Okay. So all that is to say, there's always a probability of committing an error, and that doesn't make you bad at statistics. Like it's happened. In the same way that if you're going to do a 95% confidence interval, that you've always got a 5% chance of being wrong, and that doesn't make you bad at statistics. That's just true. And it's helpful to say there's a 5% chance I'm wrong. So one thing that we can do later, and we may end up doing this in a video, is we can compute the chance of us making a type 2 error. We can compute the chance of making a type 1 error and doing hypothesis testing. And we want to do it in a way so that maybe if we want to have a less chance of being wrong, then we'll have to tweak some things. And yeah, so these are some components that are going to apply to every single kind of every single kind of hypothesis test. And in future videos, I'm going to start zeroing in on different situations that are requiring us to use specific components that aren't in this video. But The idea of null and alternative hypotheses, the two different ways of saying the conclusion, like reject H naught, don't reject H naught, and these two kinds of errors, these apply to all hypothesis tests across the board. So I hope this has been a helpful introduction, and we'll specify some things later.